Good morning, ladies and gentlemen. Today we will be graphing rational functions. Now, as you can see, I do not have a copy of the notes, so please be looking at those notes as you're working through. There's just too much for me to copy down, plus I don't have enough space on those tiny little lines that we provide you with. The first 2 pages of these notes describe how to do all of the things that I'm going to show you how to do. So I'm going to talk you through it, a few examples, but looking at what these things say is very much more helpful. So if you don't understand what I say when I say it, then look back at the first couple of pages of the notes and read what it says about finding those things. Alright, first one we're going to do is example 2b. And again, it's the same one that's on the notes, so you can either be following along with me and then seeing how I got the answers, or you can be writing this down with me as well. So this one looks like y equals 2x over x squared minus 1. And graphing rational functions, they're so odd that we need to find a bunch of different pieces and then graph those pieces to see what happens. So the first thing we're going to find are our intercepts. The y-intercept is a coordinate point when the x value is 0. So we're looking for this y value right here. To find it, plug in 0 for all your x's and simplify. If you ever have a 0 in the top, like 2 times 0, the whole thing's going to be 0. So our y-intercept is 0, 0. I like to graph as I go, so I don't have to go back and graph them all separately and get confused. There's my y-intercept, 0, 0. The x-intercept is when the y value is 0. And thinking about this, if I plugged in 0 for y here, I would have to multiply the top, or both sides, by this x squared minus 1. And if I multiply that by 0, it goes away. So really, it's just 2x equals 0. So to find the y-intercept, plug in all the zeros for x's and simplify. To find the x-intercept, set the numerator equal to 0 and solve. And guess what? We still get 0. If we have a y-intercept of 0, we have an x-intercept of 0. So these are our first 2 pieces, x-intercepts, y-intercepts. Okay, the next thing we're going to find are our asymptotes. Our vertical asymptote is the most straightforward one. It is when our function is undefined. The only way that happens is if the denominator equals 0. So we have to set up this equation, x squared minus 1 equals 0. Of course, so these are the values that it is not going to be. So we factor this, x plus 1, x minus 1 using dots. And then we separate and solve each one, and we get x equals negative 1 and x equals positive 1. These are actual equations of lines, vertical asymptotes. At 1, the function does not exist, so we draw this vertical line to know that our function cannot cross through that. At negative 1, the function does not exist, so we cross through, draw these boundary lines. Our function is going to act around these. Alright, then we've got, our vertical asymptote is also connected to any holes, and the only way we get holes is if we had in our factored form, it's often nice to write them next to each other. If we had any asymptote factors in the denominator here that canceled with factors in the top, that would produce a hole. But in this case, we have none. And the reason I'm writing this out is because this is what your test is going to look like. You're going to have all these blanks, and you just have to fill in all these spots. Alright, the next thing we need to find is our horizontal asymptote. And this is the funny saying. You remember ha, H-A makes a ha sound because it's so funny. You have to remember Bobo Button eats DC. Go back to the unfactored form, and we're looking at the first term in the top and the bottom. So 2x over x squared is the only part that matters here. Are the exponents bigger on top or bigger on bottom, or are the exponents the same? The exponent on top is 1. The exponent on bottom is 2. It is bigger on bottom, Bobo, which means y equals 0. we have a horizontal asymptote at y equals 0. Do your best to draw a dotted line on the the x-axis. If there is no horizontal asymptote, it's possible you might have a slant. So that's what this blank is for. But in this case, there is none. So that's okay. And then the only other thing we can do before graphing is talk about our domain. The domain is only restricted by these asymptotes. The function will exist over here somewhere, top or bottom. The function will exist in between here somewhere, top or bottom. And the function will exist over here, top or bottom. So therefore, the only restriction is our asymptotes. So therefore, we can write negative infinity to negative 1, our first vertical asymptote, with negative 1 to positive 1. That's in between those two. Then 1 to infinity. So that's what our domain looks like. Kind of interesting. Here's the weird part. This is a very strange graph, okay? After this one, finding all these pieces is exactly the same, but then what we need to do is interpret what our graph looks like. This right here is odd, because this point crosses through an asymptote. Horizontal asymptotes, that's okay in the middle. Horizontal asymptotes are more about end behavior. So if it crosses through in the middle, that's okay. But it's never going to cross a vertical asymptote. So what we see is we don't have any nice points to tell us where the rest of our graph goes. So we're just going to test a random point in one of these areas. Okay? So I'm going to test this point right here, x equals 2. And all I'm really looking for is it going to be above the asymptote or below the asymptote? So when I plug in 2, I get 4 over 3. What that tells me is this coordinate point, 2, 4 over 3, is about right there. All that tells me is this part of my graph is going to be a curve like this, towards my asymptotes, but not touching them, so it only exists in this quadrant. That's all we need to know. The asymptotes have a special behavior. As it approaches positive 1 from this side, it's a positive value. But when I plug in a value in between 0 and 1 here, it's going to be the opposite. It's going to give me a negative value. Because the multiplicity of this x-intercept, or sorry, asymptote is 1, these lines have to be the opposite. Okay? So notice this line's going up, this one has to go down on the other side. But we know that it crosses the x-axis here, and it can't be on the same side here, so it has to go over here. Now we also know that this x asymptote has a multiplicity of 1, so therefore it has to be on the opposite side as well. Look in the notes about multiplicity to get more information about what I'm talking about. If this was like x minus 1 squared, then it would be on the same side right here. We'll see one of those possibly here in a minute. All right, that's all we need to do. All right, next up we're going to do example 2b. Sorry. Oh, shoot. That was example 1b. My bad. I'm not rewinding, so I hope you picked up on that. Now we're going to do example 2b. Okay. We've got f of x equals x squared minus x minus 2 over x squared minus 2x plus 1. I am going to go ahead and just write out the factored form so that I can use it to help me later. The top would factor to x minus 2, x plus 1. The bottom would factor to x minus 1, x minus 1. This is what it's going to look like where your asymptote has a multiplicity of 2. We've got two factors right here, but they're the same factor, so really it's x minus 1 squared. We'll come back to that in a minute. All right, for the y-intercept, plug in 0 for x, and simplify. Hopefully by now you're noticing that just plugging in 0 for all these x's makes them disappear. And we got negative 2 over 1, which is negative 2. That makes it much easier. There's our y-intercept of negative 2. X-intercept, we're going to set the top equal to 0. So if I set this top equal to 0 right here, I'm going to end up with two x-intercepts. Positive 2 for this one, and negative 1 for that one. So 2, 0, and negative 1, 0. Again, my factored form came in really handy there. And we've been solving these for so long, I don't have to write that out separately. I know that if I set this part equal to 0, this factor is going to give me positive 2. This factor is going to give me negative 1. Those are my x-intercepts. 1, 2, negative 1. Boom. Pretty so far. Vertical asymptote. This is when we set the denominator equal to 0, so we'd have to factor it, which is the same factor, so we actually only have one vertical asymptote, x equals positive 1, with a multiplicity of 2. Sorry, I just want to highlight all the important pieces you're going to have to do on your quiz. So here's our vertical asymptote, x equals 1 with a multiplicity of 2. We'll come back to that in a minute when we start graphing. Because we didn't have any factors that canceled, see no factors canceling? Is there a hole? None. No hole. All right, HA, our horizontal asymptote. Ha! It makes me laugh. I'm thinking Bobobot needs DC. In this case, the original function is much nicer because you cover up everything except for those leading terms. And we notice the exponents are the same. That's what eats means. Exponents are the same. DC tells you to divide coefficients. 1 divided by 1 is 1. So y equals 1 is your horizontal asymptote. Because I had a horizontal asymptote, I do not have a slant asymptote. Those are coming, don't worry. And then our domain is only bounded by one asymptote, so negative infinity to 1, our vertical asymptote, then 1 to positive infinity. So, because we have this graph, and we now have points on each one, we don't have to test any points. I know that this side of my graph has to go like this through these intercepts, and I know that this side of my graph has to go through that intercept. This is what a multiplicity of 2 looks like. Since our asymptote has a multiplicity of 2 down here in the denominator, that squared right there, they have to have the same type of behavior, so they both go down. When I plug in negative values right here, I'm going to get more negative values. When I plug in positive values right here, they're going to be negative values until it switches. Cool? All right, moving on to example 3A. This one is a little bit interesting, okay? This one is a little bit interesting. 3A. F of x equals x squared plus x minus 6 over x minus 2. So, I'm going to go ahead and factor this just so we can use the factored form. X plus 3 times x minus 2 over x minus 2. This is what it looks like when our asymptote is going to cancel. A hole is going to occur. Okay? So what really happens here is this function is important, and the pieces that we find are very important, but what it simplifies to is this easy linear function. Okay? So this is actually going to come out to be a straight line, but we're going to have a hole. I'm still going to find all the pieces just like normal, so we can practice that. The y-intercept, plug in 0 for x, and simplify. So when I cover those up, I get negative 6 over negative 2, which is 3. 1, 2, 3. My x-intercept, I set the numerator equal to 0. Now, do understand though, I'm going to go with this factored form, because if I were to solve this equation, and I would have my two factors here equal to 0, this piece right here needs to be canceled out first. So we're really only looking at the x-intercept of this piece. And if you think about it, if I solved this one without canceling first, I would get x equals 2 for one of my x-intercepts. But this part right here shows us x cannot equal 2. So therefore, it's simply negative 3, 0 is our x-intercept. Okay? Vertical asymptote. We have none because it got canceled out. However, we still cannot plug in a value of 2 into my original equation, so therefore we have a hole when x equals 2. So at this coordinate point over here, we're going to have a hole. The hole will actually occur at 2, 5. The 5 comes when I plug in 2 for x up into my new function. 2 plus 3 is 5. So I'm going to have a hole right here. Okay? All right. HA, horizontal asymptote. Look at the first exponents. Bigger on top. That n means none. Okay? Bottom, the n means none. There is no horizontal asymptote, but there's also no slant because my divisor canceled. Or the bottom. And we already know that this is going to act like a linear function. That's why we know there's no slant asymptote, because it's going to be a linear function. It has to have this behavior. So there's no asymptotes whatsoever, but we do have this hole, which restricts our domain. Negative infinity to 2, 2 to positive infinity. So it acts like that. Linear function. That's a strange one. Okay, last one, and I hope this video sticks. Example 3, part B, because I just did 3A. All right, y equals 3x squared plus 7x plus 2 over x plus 1. I'm going to go ahead and factor this. 3x plus 1, x plus 2. I did not do that in my head, I just copied it down, but you should be good at factoring. Notice, nothing's going to cancel, so this is going to be strange. Or not strange, it's going to be interesting. Okay, y-intercept we should be good at by now. You plug in 0 for x and simplify. 2 over 1 is 2. X-intercept, set the numerator equal to 0. So setting these two factors equal to 0 is going to leave me with negative 1/3 and negative 2. Okay, I'm going to try and graph these. Oh, it's a terrible crooked graph. Anyway, so negative 1, negative 2. Here's my easy one. Negative 1/3 is about right there. My y-intercept right there. Okay? Alright, vertical asymptote. X equals 1, so therefore a vertical asymptote is at negative 1, setting that equal to 0 and solving. Okay. There is no hole in this case because nothing canceled. Now our HA. Cover those up. Bigger on top, none, but this is the example where we will have a slant asymptote. You will have a slant asymptote if there's no horizontal and it doesn't divide evenly. That means nothing cancels. When those canceled on example 3a, we knew that that would have divided easily, leaving us with that linear function. This is not a linear function, but nothing divides evenly, so we're going to have a slant asymptote. The way you get the equation for your slant asymptote is by using synthetic division and actually doing this division problem. So -1, 3, 7, 2. 3 comes down, -3, 4 comes down, -4, -2 is our remainder. Here's how this works. The remainder doesn't matter. These guys are 3x plus 4, so the slant asymptote is y equals 3x plus 4. It's a linear slant. It's a straight line. So 1, 2, 3, 4, down 1, 2, 3 over 1, 1, 2, 3 over 1, 2, 3 over 1. Here's what our slant asymptote looks like. Okay? Now, we can't, just like our horizontal asymptote, we can't have anything in top and bottom. Over here we can't have anything in top or in this little tiny sliver down here. So therefore, we look at the points and know that this side of our graph has to come over here. And this side of our graph is going to do this weirdness. Sorry, I graphed that one kind of strange. I should have used graph paper, but it's going to hug those asymptotes and kind of go towards them. So let's practice that more, yes, in your homework. Don't forget your domain, still only restricted by your vertical asymptote. So -infinity to -1 and union -1 to positive infinity. Please come to tutorials for extra help on this. Thank you.